In this video, we are going to talk about chapter 5 from the book, that is section 6, which is differential equation with discontinuous forcing function. Do you remember that in the spring mass system we had m and then y double prime plus gamma y prime plus ky equals to ft? This was the external force, right? And this external force can be continuous or discontinuous, okay? So for example, in the spring mass system, the external force, you can hit the mass with a hammer like for a quick, or you can keep putting the so pulling it down, and then for some time, and then you leave it, right? So those kind of external force are discontinuous. So that is the kind of concept that we are going to cover here. Let us consider a second order differential equation with constant coefficient. This is non-homogeneous because the right hand side function is non-zero. Suppose that this function gt is not continuous, okay? If the function gt is not continuous, but when you solve this whole equation, the solution you will get will be a continuous function, though. Although this second order differential equation has a discontinuous forcing function, the right hand side is discontinuous, but when you solve it, you will get a continuous function. We will take an example to see that, okay? You see that although the gt may not be continuous, but the solution of curve is continuous. For example, we are considering a function, an initial value problem, y double prime equals to u sub ct. This is basically the step function, right? Which is and also the initial condition is given as 0 and initial derivative is also 0. So we know that uct is 0 for t less than c and then 1 for t greater than c, right? How does that look like? Suppose there is c and then the value is 0, right? So the value is 0 for the value, if it is smaller than c, then it is 0, right? And if it is greater than c, then it is 1. You see that the function, the second derivative, so it is t, right? So for t is smaller than c, the function is 0, and for t is greater than c, the function is 1. The uct is defined that way, right? So y double prime is not continuous here. So on this function, y double prime is not continuous because y double prime is equals to that discontinuous function, right? So although the y double prime is not continuous, we are trying to see whether the solution of this function, which is y, is continuous or not. So first of all, what we do is we integrate this function, okay? We integrate that function in the interval 0 to t. This is what you will get. What do you get? Y prime of t minus y prime of 0 is equals to, this is a piecewise function, 0 for t less than c, and then t minus c for t greater than c. How do I get that? This is the work for that. So I integrate this equation on both sides in the interval 0 to t. This is the interval that I'm integrating, okay? When I do that, what do you get? So when I do that, you get 0 to t y double prime d tau is equals to 0 to t y c tau d tau, right? This must be tau because our limit is t, so we need to have a different variable there, okay? Now when you integrate y double prime, you'll get y prime of tau, and the limits are 0 to t equals to, this you can break into two sub intervals, right? 0 to c, because this function uct is defined that way. It is defined differently for t is less than c and differently for t is greater or equals to c. So I divided that interval into 0 to c and c to t. For 0 to c, meaning t less than c, it is 0, right? So this is 0, so what is left is only c to t. And for this interval c to t, right, so the function is uct, the value of uct is basically 1, so I replace that by 1, right? So when I do that, then if I integrate that, the integral of 1 d tau is just tau, so you plug in tau equals to t minus tau equals to c. Basically what you got is u prime of t equals t minus c, where it can be written as 0 for t is less than c and t minus c for t is greater than c. So these two are the same thing, right? Okay, if you integrate again, you will get yt minus y0 equals to c to t tau minus c d tau, which is same as 0 for t less than c, and then t minus c square over 2 for t is greater or equals to c. So if you plot this function yt equals to that thing, this is what you will get. For t is less than c, it is 0. For t is greater than c, it is a curve, like it is like a kind of a quadratic function, right? Quadratic function, because t minus c squared over 2, so it is quadratic function with kind of vertex at c, but it is only for t is greater than c. So you look like a parabola, right? Half of the parabola, half part of the parabola. You see that? So the graph of y double prime is like this, right? But you see that the graph of y prime, if you look at the graph of this function, this is also continuous but not very smooth. You see that? But if you plot the solution curve, it is smooth and continuous. So from this, what you can see here is, if the highest order derivative of a solution appearing in the differential equation has jump discontinuity like this at some point c as the forcing function, the solution and the lower order derivative of y double prime are continuous even at those points. So you can see that this was discontinuous at that point, but the lower order derivative of y prime of t, y double prime, that means y prime and then y t are continuous at c, and actually the solution curve of y double prime equals uct is even smooth. You don't have a sharp corner there, right? Even it is smooth, meaning the derivative of this is also continuous there. Okay, so this shows that if a second order differential equation has a discontinuous forcing function, the solution of that equation will be a continuous and even a smooth function. Okay, let us take an example of a second order differential equation with the forcing function as discontinuous, right? This has u2t, which is the step function, right? So what it says is, for t is less than 2, it is 0. For t is greater than 2, it is e to the 4 minus twice t. Okay, so to solve this differential equation, there is a initial condition here. One initial condition is this, and the other initial condition is that one. So to solve this differential equation, you see that we take the Laplace transform first, right? The Laplace transform of y double prime is that, and then the Laplace transform of y prime is that. You see that there is negative sign, so I put that negative and that is positive. And 5 times Laplace transform of y equals to, the Laplace transform of 4 is 4 over s, plus the Laplace transform of u2t times e to the 4 minus twice t. What I'm trying to do here is I'm trying to write this as a function of t minus 2. So what I did, I factor out negative 2. So I am able to write t minus 2. What is the reason for that? Because we know that the Laplace transform of uct times f of t minus c, if it is in this form, uct and then f of t minus c form, then we have the formula for the Laplace transform, which is e to the negative cs times Laplace transform of ft only. Okay, that's why I wanted to write in the form of f of t minus c, where c is 2. Okay, if you compare this with that one, that formula, you see that instead of c there is 2, right? So uct, there is u2t, so c is 2. Instead of f of t minus c, we have e to the negative 2 t minus 2. You see that? That's what I wrote. Take f of t minus 2 equals to e to the negative 2 t minus 2. So what is ft then? So replace t by t plus 2. It will give you, that will be just ft, right? That negative 2 and positive 2, if you replace t by t plus 2, you will get just t here, right? So, and then you get negative 2 times t. You see that? That thing will become t only, right? So when you replace t by t plus 2. So in that case, ft is e to the negative twice t. What is the Laplace transform of ft then? The Laplace transform of ft will be 1 over s plus 2, right? So e to the negative twice t has Laplace transform of 1 over s plus 2. So you can write that Laplace transform of u2t times e to the negative 2 e to the negative 2 times t minus 2 will become e to the negative 2s, right? That's what I'm using, that e to the negative 2s times 1 over s plus 2. So this is the Laplace transform of this term, right? That's how I wrote there, e to the negative 2s over s plus 2. Now what we do next is we simplify and solve for Laplace transform of y. Okay, so how much is that? So this is y0 is 2, so it will be negative 2s. That's what you get, right? This is negative 2s. And what is y prime of 0 is negative 1, so it is negative y prime of 0 will be positive 1 there, right? And then y0 is 2. That's what we use. So what do you get? You get negative 2s plus 3, right? If you move that to the other side, what do you get? 2s minus 3. So negative 2s will become positive 2s, and positive 3 will become negative 3, right? And there is 4 over s plus e to the negative 2s over s plus 2. So what is left on the left side is just that term. We got that? Okay, now you simplify these three terms here. So they have 1 in the denominator, they have s in the denominator. So how do you combine those two? Is you get 2s squared minus 3s, and then plus 4 divided by s, and that is just e to the negative 2s over s plus 2. Now to solve for Laplace transform of y, what do? Is you divide by s squared minus s plus 5 on both sides, right? What you get is 2s squared minus 3s plus 4 over s times s squared minus s plus 5 plus e to the negative 2s over s plus 2 times s squared minus s plus 5. So I assume that as a, the whole thing that I assumed as a, and then 1 over that thing will be considered as b. Okay, so bs is basically 1 over s plus 2, and then s squared minus s plus 5. I'm keeping e to the negative 2s, okay, so that when we take the inverse Laplace transform to solve for y, we will use e to the negative 2s and then some function there, and then take the inverse transform of that. Okay, so that's why I'm keeping that e to the negative 2s, and whatever left is actually bs. So bs is that value. So what we do next is we use the partial fraction for as and bs. Okay, if you use the partial fraction for that, you will get, how to use the partial fraction? You do basically a over s plus let's say c over s. Okay, because a is already used there. So you do c over s. So for that one, you do c over s plus ds plus e over, and then s squared minus s plus 5. That's what you do, right? And then you complete that partial fraction. This is what you will get. So you will get 4 over 5s. That is the value of c is 4 over 5 plus d is 6 over 5. And then e is negative 11 over 5. That's what you get. So ds plus e over s squared minus s plus 5. Okay. So now we will have to take the inverse Laplace transform. So what I'm doing is I'm trying to simplify this so that 4 over 5 times 1 over s, you can write that way, plus what I'm writing is 6 over 5. Okay, this is 6 over 5 times s minus 1/2. What I'm trying to do that is when I complete the denominator square for the denominator, that's what you will get, s minus 1/2 to the square plus 19 over 4. This is what you get when you complete the denominator. How do you get that? You write s squared minus s plus 5, right? You can write, so s minus 1/2 square will give you s squared minus 2, and then 1/2, and then s, right? So that will give you 2 and 1/2 will cancel, so that will just s. So plus 1/4, right? We need plus 1/4, but you need to subtract that 1/4. So minus 1/4 plus 5 will be 19 over 4. That's how we got that. S minus 1/2 square plus 19 over 4. If you simplify this, you will get exactly the same thing, right? So since there is s in the denominator, you want, because we know the formula is s minus b over s minus b squared plus a squared is e to the bt cosine at. Okay, so you want to write s minus b form. So what should be b then? Because when you complete the square of the denominator, you get s minus 1/2 square plus 19 over 4. So you want to write the numerator in the form of s minus 1/2. So what I did here is I pick 6 over 5 out and then write s minus 1/2, right? If you simplify this, you'll get 6 over 5s. You see that? So and then you get negative 3 over negative 3 over 10. Negative 3 over 5, right? There is negative 3 over 5, the extra thing, but we need negative 11 over 5. So what do you do then? You get negative 8. You write negative 8 over 5. So when you balance that, when you simplify that, you will get negative 11 over 5 there. Okay, now what you do next is you split. You write 6 over 5 times s minus 1 half over that, and then minus 8 over 5 times 1 over that thing. Okay, now you use the inverse Laplace transform formula. Inverse Laplace transform 1 over s is 1. Inverse Laplace transform of s minus b over s minus b square plus a square is e to the bt cosine at. But what is b? B is 1 half, a is root under 19 over 2, right? Because this is a square. You see that? So a is root under 19 over 2. Similarly, inverse Laplace transform of a over s minus b square plus a square will be e to the bt times sine at. So you take the inverse Laplace transform. This will be 4 over 5 times 1. That is basically 4 over 5 plus 6 over 5. This is cosine e to the bt cosine at, right? E to the 1 half t, that is t half, times cosine a is root under 19 over 2 times t, minus 8 over 5 is there. And then so what we need there, we need root under 19 over 2 on the top to write the sign for the inverse Laplace transform. But you can just write root under 19 over 2. So I multiply by 2 over root under 19. Okay, so 2 over root under 19. If you do that, you will get 2 over root under 19 times root under 19 over 2, right? So that will become sine root under 19 over 2 times t. So that is the inverse Laplace transform of as, right? That will be a small lowercase at. Similarly, you will get bs equals to that, and then you use the partial fraction. This is what you will get, and then take the inverse Laplace transform of bs. You will get 1 over 11 e to the negative twice t, and all those things so on, right? Now, when you take the inverse Laplace transform of this star, on the left side you will get yt. On the right side, the inverse Laplace transform of as will be just at, plus you have e to the negative 2s bs. Okay, so what is the inverse Laplace transform of e to the negative 2s bs? You see that? Inverse Laplace transform of e to the negative as times fs is uct and then f of t minus c. So uc, so what should be c here, because that negative 2, so a is 2, that's why you will get that should be at. Okay, at. So and then a there, t minus a. So here we will get, since a is 2 here, so you write u2t and then b t minus 2. You see that? So u2t b t minus 2. So on the final answer, what do you write is you write at, all those things, and then you write u2t times bt minus 2 will be all these t on the b will be replaced by t minus 2. It will be e to the negative 2 t minus 2, t minus 2 over 2, and t minus 2, t minus 2, t minus 2, like that. So that is the final answer, okay, for this